Welcome to the deep dive. Today, we're kind of putting aside the glossy ads, We want to move beyond the marketing spin and really understand the actual chemistry of how we change tooth color.
Exactly.
This is basically the shortcut. You need to be scientifically well informed on this.
Right. And well, if you're trying to understand what makes whitening successful, you really have to start with the tooth's anatomy.
Okay.
The core truth here, and it surprises some people, is that the color isn't really the enamel itself.
Ah, okay. I thought enamel was the key.
Not directly for color, no. Enamel is about 96% mineral. That makes it semi-translucent. Think of it like an optical filter.
So the dentin underneath is the real canvas, is that what you're saying?
Precisely, yes. The actual inherent color source is that softer, yellowish dentin core just beneath the enamel. It makes up the bulk of the tooth structure. So any visible color or discoloration, it's really originating there.
Right, deep inside, not just on the surface.
Okay.
Okay, let's unpack this then. If the color is trapped inside the dentin, how does a simple gel, actually penetrate that hard outer enamel layer and then chemically change what's going on underneath? That seems like a big step.
It is, but the central mechanism is oxidation. That's the key word.
Oxidation.
When you apply the active agent, and that's usually hydrogen peroxide or carbamide peroxide.
Right, those are the common ones.
Yes. It generates these highly reactive oxygen-free radicals, tiny little things, very energetic.
And what are these radicals trying to do? What are they attacking?
They specifically target complex colored organic molecules. We call them chromophores.
Chromophores, okay.
Now, what's fascinating here, scientifically, is why they're colored. It's because of their specific electron structure. They contain something chemists call conjugated double bonds. It's how they absorb light.
Okay, conjugated double bonds.
And the free radicals, they attack and break those specific double bonds. They essentially dismantle the chromophore. So by breaking them, you're turning these large, light-boarding chromophores into much smaller, colorless molecules. They also become more soluble, easier to flush out, and this fundamentally changes how the tooth absorbs and reflects light.
Leading to a whiter appearance?
Exactly. It looks whiter because it's reflecting light differently.
So if the target is these organic molecules, these chromophores, what does that tell us about which stains are easier or harder to treat?
Well, it explains everything about treatment planning, really. The chemistry works best on intrinsic stains that are organic in nature. So general yellowing, maybe from age or diet, that usually responds very well.
Okay, that makes sense.
But the grayish stains, maybe from tetracycline use during tooth formation, or sometimes from trauma where iron compounds get involved,
Yeah.
those are significantly more resistant. Their chromophores might be structured differently, or they're just more deeply embedded, perhaps within the mineral matrix itself, much harder to break down.
Gotcha. So, okay, we understand the basic chemistry is oxidation. Now, let's talk delivery. Why does the sort of physical experience of getting whitening done in the dentist's office versus using trays at home feel so different? Sometimes drastically so.
Yeah, that's really a question of chemical kinetics, the speed of the reaction. The main contrast is between hydrogen peroxide and carbamide peroxide.
Right.
Hydrogen peroxide is, well, it's direct, high impact. Use higher concentrations, it acts very fast. It delivers its full oxidative burst in maybe an hour, sometimes less.
That's the in-office stuff usually.
Typically, yes. Carbamide peroxide, on the other hand, is more of a slow-release system. It actually breaks down into hydrogen peroxide and urea.
Urea.
And that urea is important. It breaks down further into ammonia, which raises the pH around the tooth. This higher pH makes the whole process a bit gentler, safer, more stable for long, unsupervised applications, like wearing trays overnight.
So the carbamide peroxide is designed for that slower, steadier, at-home approach.
Exactly. Different tools for different situations.
But here's the thing. If the chemistry is working, whether it's fast or slow, why is that temporary sharp pain such a common side effect? Almost universal sometimes.
Right. The sensitivity. That painful syntonizing is explained by the hydrodynamic theory. That's the accepted model.
Hydrodynamic theory. Okay, what's that?
So the whitening gel itself is what we call a hypertonic solution. It's very concentrated compared to the fluid inside the tooth.
Hypertonic, meaning it has a lot of stuff dissolved in it.
Yes. And when you put this concentrated gel on the tooth surface, it creates a powerful osmotic gradient, like osmosis in biology class.
Okay, I remember that. Water moves towards the higher concentration.
Exactly. But here, the gel aggressively pulls fluid rapidly out of the dentinal tubules.
With tiny channels in the dentin.
Yes, thousands of them, leading towards the nerve, the pulp. This sudden dramatic outward flow of fluid creates pressure changes within those tubules and the nerve endings at the pulp. They detect that pressure shift and interpret it as pain, usually sharp transient pain.
Wow. So the pain is literally the tooth's fluid getting sucked out quickly by the gel. It's basically a dehydration shock at a micro level.
That's a very good way to put it. A rapid dehydration causing a pressure change that triggers the nerve response.
That's intense. But it explains why it's temporary too, right? Once the gradient normalizes.
Correct. Once the gel is removed or neutralizes, the fluid balance slowly restores and the sensitivity typically fades.
Okay, that makes so much more sense now. Bringing this all into the clinic then, for someone thinking about getting whitening done, what's the biggest planning hurdle? The thing you absolutely have to address first?
Oh, without a doubt, the critical clinical challenge is any existing dental restorations.
Meaning crowns, fillings, veneers.
Exactly. Crowns, veneers, composite fillings, anything artificial. These materials are fundamentally different from natural tooth structure. They're generally non-porous, and crucially, they are chemically inert to the whitening process. They don't have those chromophores we talked about.
So they just don't change color.
They will not change color, period, no matter how much whitening gel you put on them.
Right. So if you whiten your natural teeth,
The immediate result is an aesthetic mismatch. Your natural teeth get brighter, but your crown or filling stays the same old color. It can look quite obvious, actually.
ooh, yeah, I can see that being a problem.
It's a huge planning point. This is why the standard protocol, the mandatory way to do it right, is this. You must complete all the tooth whitening first. Get the natural teeth to the desired shade. Then you have to wait, usually about 2 weeks. This allows the tooth color to stabilize fully and for that dehydration effect to completely resolve.
Let everything settle down.
Precisely. And only then do you place any new aesthetic restorations, crowns, veneers, fillings, making sure they match that final, stable, whitened tooth shade.
So whitening always comes before new cosmetic dental work. Non-negotiable.
Absolutely. Otherwise, you're guaranteed a redo later.
Okay. So achieving that brighter smile really is, it's a careful balance then. It's optics, it's that free radical chemistry, and it's some really meticulous clinical planning.
That sums it up well. We saw color comes from the dentin deep inside, not the enamel surface.
Right.
Whitening is oxidation breaking down those conjugated double bonds in the chromophores.
Mm-hmm.
And that sensitivity, it's usually a predictable fluid shift, that hydrodynamic effect, caused by the osmotic pull of the gel.
Okay, so here's a final thought to leave you with, based on the source material. The sources we looked at consistently point out that the actual clinical effectiveness of using those special lights, the laser whitening or lead activation, its benefit is scientifically debated. And a lot of the immediate, really dramatic whitening you see right after those procedures, it's partly attributed just to temporary tooth dehydration.
Yeah, that dehydration effect we discussed can make teeth look instantly whiter, but it's not a permanent chemical change.
So if the lasting result really depends on that genuine chemical breakdown of chromophores, what does that suggest about which treatment approached the fast, high-intensity burst, often using light, or the slower, sustained chemical release might offer the most predictable, lasting result for you?
Something definitely worth considering when weighing your options.
Thanks for diving deep with us today.